Hello everyone, welcome to my channel GVS Chem. In this module, let us discuss thermodynamics enthalpy of formation. Please subscribe to my channel, like, share and comment my videos. In the previous modules, we discussed about the enthalpy change and how to find the enthalpy in a calorimeter. In this module, let us discuss the enthalpy changes, enthalpy of formation, enthalpy of reaction, and enthalpy changes during the phase transitions and others. Now, enthalpy of formation. The standard enthalpy of formation of a compound is defined as the enthalpy change accompanying the formation of 1 mole of a compound from its constituent elements in their stable state of aggregation and is denoted by delta F H naught. So the symbol for enthalpy of formation is delta F H naught, and during the formation of 1 mole of a compound from its constituent elements, then the enthalpy change is referred as enthalpy of formation. Now let us take an example. C plus O2 gives CO2. Here C solid plus O gas plus CO2 gas. So whatever the enthalpy change observed here in this reaction is called enthalpy of formation. For example, C graphite, that is allotropic form of a graphite, combines with oxygen. This is solid, graphite is in solid and oxygen is in a gaseous state. We get carbon dioxide is gas, and here enthalpy change is minus 393.5 kilojoule, of course, per mole. So in this reaction, carbon dioxide is obtained from its constituent elements. Therefore, enthalpy of formation of carbon dioxide is referred as minus 393.5 kilojoule. Here three equations are given: Ca2 plus calcium ion plus a carbon dioxide ion. In their aqueous solutions, they combine to form calcium carbonate, a precipitate that is solid. Here the enthalpy change is minus x kilojoule per mole. In the second equation, calcium, this is element, graphite, carbon, this is element, and oxygen element. So calcium plus carbon plus oxygen, they combine and we get the calcium carbonate solid, and here delta H change in enthalpy equal to minus y kilojoule per mole. In the same manner, in third equation, calcium oxide, which is a compound, calcium oxide combines with carbon dioxide is another compound, and we get calcium carbonate. And change in delta H is change in enthalpy is minus Z kilojoule per mole. In all these three equations, three reactions, calcium carbonate, that is limestone, is formed. But out of these three, only in second equation the compound is formed from its constituent elements. Therefore, this reaction, it is the enthalpy change involved in the second reaction is referred as enthalpy of formation. So here enthalpy of formation of calcium carbonate is minus y kilojoule per mole. So from this it is understood that if a compound forms from other compounds, then the enthalpy change involved is not the enthalpy of formation. For example, in third equation, enthalpy change is minus Z kilojoule per mole. This is not the enthalpy of formation. While learning the standard enthalpy of formation, certain points should be kept in mind. That is, the reference state or standard state of element is the pure element in its most stable state at 298 Kelvin and 1 bar pressure. Say whatever the state of the element available are present at normal conditions of temperature and pressure, that is 298 Kelvin and 1 bar, that is the standard state or reference state of the element. Now let us see the different elements and their reference states. Carbon the reference state is taken as a graphite. Sulfur, the reference state is rhombic. Oxygen, the reference state is O2 gas, and bromine is liquid, so Br2 liquid. Now, the standard molar enthalpy of formation of free elements in their reference state is taken as 0. As per convention, the standard molar enthalpy of free elements in their reference state is taken as 0. For example, delta FH naught of oxygen is 0. Similarly, hydrogen is 0. Rhombic sulfur is 0. Bromine is 0. So, the standard molar enthalpy of free elements in their reference state is taken as 0. Now, the standard molar enthalpy of formation of a substance is also referred as a standard enthalpy. See, we may not pronounce every time the standard molar enthalpy. Instead, we can cut short as standard enthalpy and denoted by delta H naught. Delta FH naught to find. See, the significance of the standard formation, standard molar enthalpy of formation is to find the standard enthalpy change of reactions. Enthalpy change taking place in different reactions is calculated by using standard molar enthalpies of different substances. So, enthalpy change taking place in a reaction, enthalpy change equal to sigma delta FH naught products minus sigma delta H F naught reactants. Sigma means the sum of the enthalpies of formation of all the products. That is nothing but sum of the enthalpies of formation of all products minus sum of the enthalpies of formation of all reactants. Formation of all reactants. Let us take an example here. C2H4 gas plus O2 gas gives 2CO2 gas plus 2H2O liquid. So, delta RH. What is delta RH? Enthalpy change taking place in the reaction. Delta H equal to sigma delta FH naught products minus sigma delta FH naught reactants. So what are the products here? Products is ethylene and oxygen. So delta FH naught of C2H4 gas plus oxygen 3 moles are there, therefore 3 into delta FH naught of oxygen minus the products are carbon dioxide and water, therefore 2 moles of carbon dioxide are there, therefore this is 2 into delta FH naught of CO2 plus oxygen water 2 molecules are there, therefore 2 into delta FH naught of water. So in this way we can find the enthalpy change taking place in a reaction by using the enthalpies of formation of different substances. Now let us do a small problem. The standard enthalpies of formation of 4 substances, ozone, calcium oxide, ammonia and hydrogen iodide are 142.2 minus 634.9 minus 46 plus 25.95 kilojoule per mole respectively. Arrange them in order of increasing stability with respect to their decomposition into elements. First of all, let us write the data and let us try to understand. So, compound and energy change. Compound O3 and here this is plus 142.2, calcium oxide minus 634.9, ammonia minus 46 and hydrogen iodide plus 25.95. So we know that negative sign indicates the energy releases. Energy releases. So during the formation of calcium oxide, energy releases means it is highly stable, and during the formation of compound ozone, it is a plus 142. That means it takes energy. So negative sign indicates release of energy and positive sign indicates absorption of energy during the formation. Therefore, compound with more negative value is most stable. Now let us write the increasing order of stability. Increasing order of stability means least stable to highest stable we have to write. Because ozone has a positive value in a higher level, therefore this is least stable. Ozone is less than, followed by hydrogen iodide, followed by ammonia, followed by calcium oxide. So among all these, calcium oxide is most stable, therefore it does not decompose into its elements. Let us do one more problem. The enthalpy of combustion of acetic acid is given as follows. CH3COOH plus oxygen gives CO2 plus water. Delta H, that is enthalpy change of reaction, is given as minus 867 kilojoule per mole, and the enthalpies of standard molar enthalpies of formation of carbon dioxide and water are minus 395.5 and minus 289.0 kilojoule per mole respectively. Calculate the enthalpy of formation of ethanoic acid. So here delta RH, that is enthalpy of reaction, is equal to sigma delta H formation products minus sigma delta H formation enthalpy of formation of reactants. So reactants equal to, what are the products? Carbon dioxide and water. So 2 moles of carbon dioxide, 2 into delta HF carbon dioxide plus 2 moles of water, 2 into delta FH water. This is minus products. What are the products? Acetic acid and oxygen. Therefore, delta FH CH3 COOH plus 2 into delta FH oxygen. So this is, now this value is nothing but enthalpy of formation of enthalpy of reaction. What is the enthalpy of reaction? Minus 867.0 is equal to 2 into enthalpy of formation of carbon dioxide is nothing but minus 395.5 plus enthalpy of water is nothing but minus 289. So this is 2 into minus 289 minus of acetic acid. This we have to find delta F H naught of CH3COOH plus oxygen being element, its enthalpy of formation is 0. Therefore, minus 867.0 is equal to 2 into this much. How much this is? 1, 10, 11, 18, 19. This is 7. Minus 799, 791 plus. This is 18, 7, 5. Minus 578 minus delta F H naught of CH3 COOH minus 867.0 is equal to, here 0.1, 9, 9 plus 9, this is 7, 7 plus 9, 16, this is 13, minus delta HF CH3 COOH. So this is, bring this to this side, standard enthalpy of formation of acetic acid equal to, this is total minus 1369.1, bring this minus to this side, it becomes plus 867.0. So this is 502.1 kilojoule per mole. Now let us discuss about the enthalpy change of a reaction. Enthalpy change accompanying the chemical reaction when the molar quantities of reactants and products are the same as indicated in the chemical reaction. So enthalpy change of a reaction is denoted as delta HR. Under standard conditions, this is a standard enthalpy, is equal to sigma enthalpy of formation of products. Sum of the enthalpies of products minus sigma delta HF. This is sum of the enthalpy formations of reactants. Now, enthalpy change of a reaction depends on different factors. So, factors on which enthalpy change of reaction depends. Number one, physical state of the reactants and the products. Second one is quantity of reactants. If the quantity is more, enthalpy change is more, and if quantity is less, enthalpy change is less. Next one is allotropic modifications. Some of the nonmetals, they exist in allotropic forms. For example, carbon has 2 allotropic forms, diamond and graphite. Sulfur has 3 allotropic forms, rhombic, monoclinic and plastic. So depending on the allotropic form, the enthalpy change depends. And finally, the temperature. So these are the factors on which the enthalpy of a reaction depends. Now let us discuss the enthalpy changes during phase transition. Phase transition means change of one state of substance to another state. So phase transitions are solid to liquid, liquid to gas or vapor, and solid to vapor. So there are 3 phase transitions, solid to liquid. So enthalpy change taking place from solid to liquid is referred as enthalpy of fusion, and here liquid to gas it is enthalpy of vaporization, and from solid to vapor it is enthalpy of sublimation. Let us discuss the enthalpy of fusion. The standard enthalpy of fusion is the enthalpy change accompanying the melting of 1 mole of solid substance in its standard state at its melting point. So this is the enthalpy of fusion. Now let us take an example, water solid. Water solid means it is nothing but ice. So this water solid, it changes to liquid. So this is H2O liquid. So here delta H fusion, enthalpy change of fusion is equal to plus 6.0 kilojoule per mole. So here plus indicates absorption of heat, absorption of energy. But are we supplying this energy to the ice? We are not supplying. Even if you keep a piece of ice in a normal temperature in a dish, in a vessel, it changes to ice because it takes the required amount of heat energy from the atmosphere itself. So in the atmosphere itself at 298 Kelvin and 1 bar pressure, certain amount of energy is available, and that available energy is taken by ice and it melts to water. Now let us discuss the standard enthalpy of vaporization. Molar enthalpy of vaporization is the enthalpy change accompanying the evaporation of 1 mole of liquid substance in its standard state into its vapors at a boiling point and at 1 bar pressure, and of course it is denoted by delta H vaporization. So the example for this delta H vaporization is water liquid. At normal temperature it changes to water, gas. Gas means vapors. Keep the point in mind. Therefore, delta H vaporization is equal plus 40.6 kilojoule per mole. Plus 40.6 kilojoule per mole. So, evaporation takes place at normal temperature. Therefore, it takes energy from atmosphere. Whereas, if we bring the water to high temperature, then it boils. So, that is enthalpy of vaporization. Now, let us see the enthalpy of sublimation. Standard or molar enthalpy of sublimation is the enthalpy change accompanying the sublimation of 1 mole of a solid substance into its gaseous state at a constant temperature below its melting point. That means, if a solid substance is exposed to air, it changes to vapor before reaching its melting point. The best example is camphor. So, camphor, when it is kept in open air, it changes to vapors at normal temperature itself. That's why camphor is used for preserving the clothes. Therefore, here the example is iodine. Iodine is solid. Solid iodine changes to vapors, gaseous, dark violet vapors. So, delta H sublimation is equal to plus 62.4 kilojoule. So, all these phase transitions, they are endothermic reactions. That is, they absorb heat from the atmosphere. Therefore, one state of the substance changes to another state. That is, solid to liquid, liquid to vapor, and solid to vapor. Now, let us do some problems based on enthalpy of formation, enthalpy of reaction, and enthalpy changes involved in phase transition. Now, the problem here is the standard enthalpy of evaporation of benzene at the boiling point is 30.8 kilojoule per mole. How long would a 100-watt electric heater have to operate in order to vaporize a 200-gram sample at that temperature? Now here, this is delta H vaporization is equal to 30.8 kilojoule per mole. What is the molar mass of benzene? Molar mass of benzene C6H6 is equal to 78 gram mole. So, 78 grams of benzene needs 30.8 kilojoule to vaporize. Now, what is the given substance? Given mass is equal to 200 grams. Given mass equal to 200 grams. Therefore, number of moles equal to weight by molar mass. Weight how much? 200. 200 by 78. So, this is the number of moles. So, here 1 mole of benzene needs 30.8 kilojoule. Number of moles here, this is 2.56 need how much? So, this is 30.8 into 2.56 kilojoule. Now, power of heater is 100 watt. 1 watt equal to 1 joule by 1 second. So, power equal to work by time. That is, implies 1 watt equal to 1 joule per second. Now, 100 watts equal to 100 joule per second. Now, heat required equal to 2.56 mole, 2.56 mole into 30.8. So, time equal to energy by power. Energy how much? 2.56 into 30.8 kilojoule by power 100 joule per second. See here, this is in kilojoule, this is in joule. Therefore, we must convert kilojoules into joules. Therefore, this is equal to 2.56 into 30.8 into 10 to the power 3 joule by 100 joule second. So this is nothing but 2.56 into 30.8 into 10 second. So this can be written as 2.56 into 30.8 into 10 by 60 minutes. So this is equal to, so the final answer is 13.14 minutes. Standard enthalpy change of the reaction is equal to sigma delta FH products minus sigma delta FH reactants. So what are the products here? Is equal to, products are nitrogen and water. Therefore, 1 by 2 delta FH nitrogen plus 3 by 2 delta FH enthalpy of formation of water minus of reactants. Reactants are ammonia and oxygen. So ammonia only one molecule is there. Therefore delta FH NH3 plus 3 by 4 delta FH of oxygen. Now we know that enthalpies of formation of elements under their standard conditions are 0. Therefore, for nitrogen, this is nitrogen, enthalpy of formation of nitrogen is 0 and that of oxygen is also 0. Therefore, 0 plus 3 by 2, enthalpy of formation of water is minus 286.0 minus of delta H for ammonia minus 46 plus this oxygen is 0. Therefore, this is 0. This is nothing but 3 times 2, 146. 3 into 143 minus of minus is plus 46. This is minus. So this is nothing but 9, 12, 4 minus 46. This is 3. This is plus and of course this is minus. 9 minus 6 is 3. 12 minus 4 is 8. This is 3. Minus 383 kilojoule per mole. In the next module, let us discuss Hess law and its applications. Please subscribe to my channel, like, share and comment on my videos. Thank you.